All right, so here's a robot that we built. We have 3 joints, and on top of these joints, we have coordinate systems that we have. And you have the z-axis, which is going to be along the joint axis. The x-axis is going to be along the common normal, and the y-axis is going to be in correspondence to the right-hand rule. So, aside from the 3 coordinate systems we have a coordinate system here as well, and that's going to be translated from this third joint. It's going to shift over, and it's going to shift down to represent the tooltip, the end of the tooltip. And then we have this coordinate system right here, which is our frame of reference. That just got shifted from our base to here. So we have a point right here on the board that we picked. And we picked this because if we move this joint negative 90 degrees, we will reach this point right here. This joint didn't move at all. This joint right here didn't move at all. So our joint angles are going to be 0, negative pi over 2, and 0. Now, if we plug those values into MATLAB for the forward kinematics, it's going to give us the end effector location in correspondence to this frame. And the way it does that is it's going to give us a transformation matrix. And in that transformation matrix, we're going to also have a translation matrix. That's going to have our x, y, and z direction. If we take the x and y direction and the values for those, we can put them in the distance formula, and we're able to get the distance from this frame of reference to this point right here. And then we also measured using a ruler from this frame of reference to this point right here. And we were able to compare those 2 values that we got using our error function, and that tells us how close we actually were to the correct values.
In addition to our coordinate system and board the robot we built on the board, we also created a GUI and a model in MATLAB. So as you can see here, if we run the project file, the GUI will pop up. And if we hit create robot right here, it will create the model of our robot in MATLAB right here. So you can see a model of our robot. And you can move it around, rotate it, and look at the different axes and different angles. In addition to that, we also added some joint angles in here. So we can move, if you slide this, it corresponds to the second joint angle, and it will rotate it however much you want to rotate it. We have that for each angle. And in addition to that, if you hit use keys right here, it will allow you to use the keyboard keys, the arrow keys on the keyboard, to move the position of the end effector in the x and the y directions, and that is in the x and y directions from our frame of reference. So if we rotate it around, and you can see the x and the y axes, you can see that right now I'm moving it in the negative x direction or the positive x direction. I can also go in the negative y and positive y. It moves 0.2 centimeters per every time you click the keys. And in addition to that, we also have, if you look here at our DH parameters, these are our original DH parameters that we measured physically on the board. The first value is the link length, then the link twist, and then the distance d between the origins, the link offset, and that's for the first 3 are for the first joint, the second 3 are for the second joint, and the third 3 are for the last joint. So if we run the error function on our original DH parameters, which will compare these, we had our pre-measured values on the board for 5 different points. We measured the distance, and then using the forward kinematics, we got the transformation matrix and the x and the y, and we calculated the distance in this MATLAB function, and it'll output the average error between our measured values on the board and the MATLAB's model's error. And as you can see here, it's 1.5 centimeters. But if we utilize that error function here in this optimize, this fmin search, it will optimize these DH parameters. And if we run this right now, it will give us optimized DH parameters that will be slightly different than ours. As you can see here, there's some slight changes between the values, but they remain pretty small. And then if we run the error function on these new DH parameters, it went down from 1.5 centimeters to 0.3 centimeters, so significantly optimized.